Welcome to Module 3, Knowledge Representation and Reasoning. In this module, we are moving into one of the classical foundations of artificial intelligence, the question of how a machine can hold knowledge in a form that it can actually use. Up to this point, it is common to think of artificial intelligence mainly in terms of prediction, pattern recognition, or models trained from data. But intelligent behavior also depends on how information is organized, connected, and made available for reasoning. A system may have access to facts, observations, rules, and relationships, yet those pieces only become useful when they are represented in a structure that supports interpretation. That is why knowledge representation matters. It gives artificial intelligence a way to treat information not merely as stored content, but as a basis for drawing conclusions and making decisions. When we talk about knowledge representation, we are asking how a machine can model the world in a disciplined way. Human beings do this constantly without noticing it. We understand that a person can be a student, that a student can be enrolled in a course, that a course can have prerequisites, and that those relationships imply certain constraints and possibilities. An artificial intelligence system needs some formal version of that same organization if it is going to reason beyond isolated pieces of data. It needs to know what things are, how they relate, what conditions apply, and what follows when those conditions are satisfied. The challenge is not simply to store information, but to store it in a way that supports meaningful action. This is where reasoning enters the conversation. Reasoning is the process that allows a system to move from what is already represented to what can be concluded from it. If the system knows that all patients with a certain combination of symptoms should be evaluated for a particular condition, and it also knows that a specific patient has those symptoms, then it can infer that the evaluation should be considered. That example is simple, but it captures the basic movement from knowledge to conclusion. In symbolic artificial intelligence, that movement is often made explicit through logic, rules, and structured frameworks that allow the system to explain why a conclusion was reached. This is very different from treating the model as a black box, because the reasoning path can often be examined, challenged, and refined. As we work through this module, keep in mind that knowledge representation and reasoning are not just historical topics, even though they are deeply connected to early artificial intelligence. Expert systems, rule-based systems, and logical representations shaped some of the first serious attempts to build machines that could emulate expert judgment in domains such as medicine, engineering, and diagnostics. Those systems showed that carefully encoded knowledge could produce useful decisions within well-structured environments. At the same time, they also revealed the limits of symbolic approaches, especially when the world becomes ambiguous, incomplete, changing, or difficult to reduce to clean rules. So the goal here is not to treat symbolic reasoning as either outdated or perfect, but to understand what it makes possible and where its boundaries appear. Another important idea is that representation choices are never neutral. When designers decide to use logic, rules, categories, or structured relationships, they are also deciding what the system will be able to express. Some representations are excellent for precision and consistency, while others are more flexible but harder to inspect. A rule-based system can make a decision transparent by showing the rule that fired, but it may struggle when the case does not fit the rule cleanly. A logical framework can support rigorous inference, but it depends on the quality and completeness of the knowledge supplied to it. This is why knowledge representation is both a technical problem and a design problem, because the structure of knowledge determines the shape of the reasoning that follows. By the end of this module, you should be able to see knowledge representation as a central design issue in artificial intelligence. The way knowledge is represented shapes what the system can notice, what it can ignore, what it can infer, and how clearly it can justify its decisions. Logical representations help create consistency. Rule-based systems make expert knowledge operational. Structured knowledge frameworks allow relationships and conditions to be modeled in ways that support automated reasoning. As we begin, I want you to listen for that larger theme. Intelligent systems do not only need data, they need organized knowledge, and they need reasoning processes that can transform that knowledge into conclusions. That relationship will guide the entire discussion. Knowledge representation is one of the foundations of artificial intelligence because it answers a basic question that every intelligent system has to face. How should knowledge be stored so that it can be used? It is not enough for an AI system to contain raw facts, labels here, observations, or records. Those pieces of information have to be arranged in a form that preserves meaning, connects related ideas, and allows the system to act on what it knows. In that sense, knowledge representation is the bridge between information and intelligence. It gives the system a structured way to hold facts about the world, organize those facts into meaningful relationships, and manipulate them when a new question, problem, or decision appears. When an artificial intelligence system stores information, it is doing more than saving data in memory. Storage becomes valuable only when the information is accessible in a meaningful form. For example, a system that records that a patient has a symptom, that the symptom is associated with a condition, and that the condition requires a certain evaluation is not merely preserving separate statements. It is building a usable structure of knowledge. That structure allows the system to retrieve relevant details, compare them with other details, and recognize which pieces matter in a specific context. Without representation, the information may exist, but the system has no reliable way to use it intelligently. The second role of knowledge representation is organization. Artificial intelligence systems often need to work with many pieces of information at the same time, and those pieces are rarely independent. A course may belong to a program. A program may have required outcomes, and an assignment may be designed to assess one of those outcomes. A knowledge representation allows these relationships to be expressed clearly so the system can understand how one concept depends on, constrains, or supports another. This kind of organization matters because reasoning usually depends on relationships rather than isolated facts. The system needs to know not only that something is true, but also how that truth connects to other truths. The third role is manipulation, and this is where representation becomes especially important for reasoning. Once knowledge has been structured, an AI system can operate on it. It can compare conditions, apply rules, search for missing information, test whether a conclusion follows, or update what it knows when new evidence becomes available. This is the difference between a system that simply reports information and a system that reasons with information. If the representation is well designed, the system can move from stored knowledge to useful conclusions in a way that is consistent and in many cases explainable. Structured representations support effective reasoning because they give the system something stable to reason over. A logical representation can make relationships explicit enough for formal inference. A rule-based representation can express expert knowledge in conditional form so that when certain conditions are present, certain conclusions or actions become appropriate. A structured framework can organize concepts into categories, attributes, and relationships, making it easier for the system to navigate complex knowledge. In all of these cases, the structure is doing real work. It limits ambiguity, clarifies connections, and allows the system to process knowledge in a disciplined way. This structure also supports decision making. Decisions require more than information. They require an understanding of conditions, consequences, and possible actions. An AI system that recommends a diagnosis, flags a risk, selects a strategy, or identifies a next step has to connect what it knows with what should be done. Knowledge representation provides the internal model that makes that connection possible. It allows the system to treat knowledge as actionable rather than passive. The better the representation captures the relevant relationships and conditions of the domain, the more effectively the system can support intelligent decision. So, as we begin this learning objective, treat knowledge representation as a central design layer in artificial intelligence. It's the layer that makes information usable, organizes knowledge into meaningful structures, and gives the system a basis for reasoning and decision making. When AI models real-world relationships and conditions using structured knowledge, it gains the ability to draw connections, evaluate situations, and support decisions in a way that raw data alone cannot provide. This is why knowledge representation is not just an early topic in the history of AI. It remains one of the core ideas behind any system that needs to know something, reason from what it knows, and act intelligently on the basis of that knowledge. When we compare symbolic knowledge representation techniques, we are comparing different ways of making knowledge explicit enough for a machine to reason with it. Symbolic artificial intelligence starts from the idea that parts of the world can be represented using symbols, relationships, and formal structures. Instead of relying only on numerical patterns, the system works with statements, rules, categories, and connections that have interpretable meaning. This is why symbolic techniques have been so important in areas where we need clarity, consistency, and the ability to inspect how a conclusion was reached. They give us a way to organize knowledge so that automated reasoning becomes possible rather than accidental. One major symbolic technique is logical representation, where knowledge is expressed in a form that supports formal inference. In a logical representation, the system might encode facts about entities, properties, and relationships, and then use rules of logic to determine what follows from those facts. This approach is powerful because it allows the system to draw conclusions that are not directly stated, but are implied by what is already known. For example, if the system represents a general relationship and then receives a specific case that fits that relationship, it can infer a new conclusion from the combination. The value of logic is that it gives reasoning a disciplined structure, so the system is not merely guessing, it is applying formal relationships. Rule-based systems are another important symbolic technique, and they organize knowledge in a more procedural way. Instead of representing knowledge primarily as logical formulas, a rule-based system captures expertise through conditional statements, often in the form of if certain conditions are true, then a particular conclusion or action should follow. This makes rule-based systems practical for domains where experts can describe decision patterns clearly. A diagnostic system, for instance, might use rules that connect symptoms, measurements, and risk factors with possible interpretations. The strength of this approach is that the reasoning path can often be traced through the rules that were applied, which makes the decision process easier to explain and review. Structured knowledge frameworks provide a third way to represent symbolic knowledge, and they focus on organizing concepts, categories, attributes, and relationships. These frameworks can include structures such as semantic networks, frames, and ontologies, depending on the level of formality and detail needed. What they share is the goal of modeling knowledge as a connected structure, rather than as a loose collection of statements. A concept can belong to a larger category, inherit properties from that category, and be linked to other concepts through meaningful relationships. This kind of representation is useful when the system needs to understand how ideas are connected across a domain, not simply whether one isolated rule applies. The important comparison is that these techniques all support automated reasoning, but they do so in different ways. Logical representations emphasize formal consistency and inference, making them well suited for situations where conclusions need to follow rigorously from stated knowledge. Rule-based systems emphasize expert decision patterns, making them useful when knowledge can be captured as condition-action relationships. Structured knowledge frameworks emphasize organization and relationships, making them valuable when the system needs to represent a larger domain with many connected concepts. So the question is not which technique is universally best, but which representation best fits the kind of knowledge and reasoning the system needs. Each approach also shapes what the AI system can do well and where it may struggle. Logic can be precise, but it depends on carefully defined statements and may become difficult to manage as domains grow more complex. Rule-based systems can be transparent and practical, but they may become brittle when cases fall outside the rules that were originally encoded. Structured frameworks can represent relationships richly, but they require careful design so that the categories and connections remain meaningful. These trade-offs matter because representation is not just a storage decision. It determines the reasoning behavior that becomes available to the system. As we move through this learning objective, keep the comparison grounded in the slide's idea. Symbolic techniques model real-world knowledge in structured forms. Whether we use logic, rules, or knowledge frameworks, we try to give a machine a representation that supports reasoning rather than simple retrieval. The system needs to organize information so that it can evaluate conditions, connect concepts, and reach conclusions in a controlled way. That is the continuing contribution of symbolic knowledge representation. Logical reasoning is the process that allows an artificial intelligence system to move beyond what has been explicitly stored and toward what can be concluded from stored knowledge. This is a major shift in capability. A system that only retrieves information can answer questions by looking up what is already there, but a reasoning system can examine relationships, apply rules, and infer something not written as a separate fact. That ability is central to machine intelligence because many decisions require more than recall. They require the system to recognize that facts, considered together, imply a conclusion. In symbolic artificial intelligence, logical reasoning works because knowledge has been represented in a structured form. The system may store facts about objects, people, events, conditions, or relationships, and it may also store general principles that explain how those facts should be interpreted. Once knowledge is represented this way, the system can evaluate whether a conclusion follows from what it knows. If the system knows that a condition leads to a required action, and it also knows that the condition is present in a case, then it can infer that the action is appropriate. The conclusion depends on the structure of knowledge and the reasoning rules applied to it. This kind of reasoning supports the evaluation of possible conclusions. In real decision environments, there may be several conclusions that appear plausible at first. A machine has to compare those possibilities against the knowledge it has available. Logical reasoning gives the system a disciplined way to test whether each possible conclusion is supported, contradicted, or left uncertain by stored knowledge. That matters because intelligent decision-making is not simply about producing an answer quickly. It is about producing an answer that follows from the available information in a consistent and defensible way. Logical reasoning also helps machines determine appropriate actions. Once a system can infer what is likely, required, permitted, or prohibited, it can connect knowledge to action. In a diagnostic context, the action might be to recommend further evaluation. In a planning context, it might select a next step that satisfies conditions. In an automated support system, it might route a case, flag a risk, or apply a policy. The important point is that the action is not chosen randomly or only because of a surface pattern. It is chosen because the system can reason from what it knows to what should happen next. Drawing conclusions from existing knowledge is powerful because it allows an AI system to generate new, usable information without being told everything directly. Human experts often reason this way. They combine general knowledge with details from a specific situation and then reach a conclusion that was not explicitly stated at the beginning. Logical reasoning gives machines a formal version of that process. If the knowledge base is accurate and the reasoning rules are appropriate, the system can extend its knowledge by identifying what follows from what is already represented. At the same time, logical reasoning depends heavily on the quality of the stored knowledge. If the representation is incomplete, inconsistent, or poorly designed, the conclusions may be weak or misleading. This is why knowledge, representation, and reasoning cannot be separated. The system reasons over the knowledge it has, so the clarity of the representation affects the quality of the inference. Logical reasoning can be rigorous, but rigor does not guarantee truth if the underlying knowledge is wrong or too limited. A valid inference can still rest on flawed assumptions, and that limitation matters. Structured reasoning enables intelligent decision-making because it creates a traceable path from knowledge to conclusion. In domains involving policy, safety, medicine, engineering, or compliance, it is not enough for a system to provide an output. We often need to know how the output was reached. Logical reasoning helps because it allows the reasoning process to be examined. Which facts were used, which rules applied, and why a conclusion followed. This explainability is one of the strongest advantages of symbolic reasoning, particularly compared with systems whose internal process may be harder to interpret. So, as we analyze logical reasoning, focus on the movement from stored knowledge to inferred conclusion. The system begins with represented facts and relationships. It evaluates what those facts imply. It considers possible conclusions and identifies which ones are supported. It can then determine an appropriate action based on that reasoning. That sequence is what makes logical reasoning so important in artificial intelligence. It transforms knowledge from a static resource into an active foundation for decision making, allowing machines to reason in a way that is structured, consistent, and often explainable. Expert systems and rule-based systems are important because they show how early artificial intelligence tried to capture expert decision making in a structured form. Instead of asking the machine to learn patterns from massive amounts of data, these systems began with knowledge supplied by human experts. That knowledge was translated into rules that the computer could apply consistently when a case matched certain conditions. In this sense, the system was not intelligent because it had human judgment. It was intelligent because it could apply organized expert knowledge to a defined problem and produce a reasoned conclusion. The basic idea behind an expert system is that expertise can be represented as a set of relationships between conditions and conclusions. A physician, engineer, or diagnostic specialist often makes decisions by noticing patterns, comparing them with prior knowledge, and deciding what those patterns imply. Early AI researchers tried to make part of that reasoning explicit. They would work with domain experts to identify the facts that matter. the conditions under which those facts become significant, and the conclusions or recommendations that should follow. Once that knowledge was encoded, the system could reason through new cases using the same structured knowledge base. Rule-based systems are closely connected to this approach because rules provide the operational mechanism for reasoning. A rule might express that when symptoms appear together, a possible diagnosis should be considered, or when a measurement exceeds a threshold, an engineering component should be inspected. The specific domain can change, but the reasoning structure remains similar. The system checks whether the conditions of a rule are satisfied, and when they are, it applies the conclusion or action associated with that rule. This gives the AI system a clear decision path, because the reasoning depends on identifiable rules rather than hidden internal associations. The fields listed on this slide help us understand why these systems were attractive in early AI. Medicine, engineering, and diagnostics are domains where specialized knowledge matters and where decisions often depend on recognizable conditions. In medicine, an expert system could help organize symptoms, test results, and clinical rules into a possible recommendation. In engineering, rules could capture safety tolerances, design constraints, or troubleshooting steps. In diagnostics, whether medical or technical, the system could work through evidence and identify likely causes. These are domains where structured reasoning seemed promising because expert knowledge could be broken into smaller decision rules. What made these systems especially valuable was their ability to automate reasoning in controlled settings. Once the rules were encoded, the system could apply them repeatedly and consistently. It did not get tired, forget a step, or overlook a rule because of distraction. It could also provide transparency because the conclusion could often be traced back to the rules that fired during the reasoning process. That made expert systems attractive in environments where people wanted more than an output. They wanted to understand the basis for the recommendation. The system could show a chain of reasoning that connected the initial facts to the final decision. At the same time, evaluating these systems means recognizing their limitations. Expert systems work best when the domain is stable, the knowledge can be clearly articulated, and the decision process can be represented through rules. They struggle when knowledge is incomplete, ambiguous, changing, or dependent on context that is difficult to formalize. Human experts often rely on experience, judgment, and subtle cues that may not translate neatly into conditioned action rules. As the number of rules grows, the system can become difficult to maintain because new rules may conflict with older ones or create unexpected paths. So the same structure that gives these systems clarity can also make them rigid. This is why expert systems are best understood as early but serious AI implementations. They demonstrated that machines could use structured knowledge to perform useful reasoning in specialized domains. They also helped establish ideas that remain important today, including knowledge bases, inference mechanisms, and explainable decision paths. Even though modern AI often emphasizes machine learning and data-driven models, rule-based reasoning still appears in many practical systems, especially when consistency, transparency, and compliance matter. So when we evaluate rule-based systems and expert systems, we are not simply looking at old technology. We are examining a foundational approach to artificial intelligence that showed how encoded knowledge could become automated reasoning and how structured rules could turn expert understanding into machine-supported decisions. Symbolic reasoning approaches are valuable because they give artificial intelligence systems a structured way to represent knowledge and a disciplined way to use it. In these systems, knowledge is not treated as an unorganized collection of facts. It is represented through symbols, rules, logical relationships, and structured categories that allow the machine to reason over what has been stored. This is one of the major strengths of symbolic AI. The system can often show how it moved from a set of facts to a conclusion. When decisions need to be consistent, explainable, and grounded in knowledge, symbolic reasoning provides a powerful foundation. One advantage of symbolic reasoning is consistency. If a rule or logical relationship has been defined clearly, the system can apply it the same way each time the relevant conditions appear. That matters in domains where decision-making should not vary randomly from one case to another. A rule-based system that checks safety conditions, eligibility criteria, diagnostic indicators, or compliance requirements can apply the same reasoning pattern across many cases. This kind of consistency is especially useful when the domain is well understood and the rules are stable. The system does not depend on intuition or hidden associations. It depends on explicit structures that guide the reasoning process. Another advantage is explainability. When a symbolic system reaches a conclusion, it is often possible to inspect the reasoning path. We can ask which facts were used, which rules were triggered, and which logical relationship supported the result. This makes symbolic reasoning attractive in settings where people need to trust, audit, or challenge the output of an AI system. In medicine, engineering, education, policy, or legal compliance, a conclusion without an explanation may not be enough. A symbolic approach can provide a traceable connection between stored knowledge and the decision produced, and that traceability is one reason these approaches remain important. Rule-based approaches are also effective at encoding expert knowledge. Many expert tasks involve patterns that experienced professionals can describe as conditional judgments. If a certain combination of symptoms appears, consider a possible diagnosis. If a component behaves in a certain way, inspect a particular subsystem. If a learner demonstrates one skill, but not another, recommend a targeted intervention. These examples show why rules can be useful. They allow human expertise to be converted into a form that machines can apply. In a structured domain, this can make expert reasoning more scalable, consistent, and easier to share. However, symbolic reasoning also has limitations, and those limitations are important to evaluate honestly. These approaches depend heavily on the quality, completeness, and accuracy of the knowledge representation. If the rules are incomplete, the system may fail to recognize cases that fall outside what designers anticipated. If the categories are too rigid, the system may struggle with situations that are ambiguous or context dependent. If the logic is built on assumptions that no longer hold, the reasoning may remain internally consistent while still producing poor conclusions. Symbolic reasoning can be precise, but precision does not automatically make the system adaptable. Another limitation is brittleness. A symbolic system may perform very well in a narrow structured domain, but struggle when the environment becomes messy, uncertain, or rapidly changing. Human reasoning often tolerates incomplete information and can adjust when a situation does not fit a familiar pattern. A rule-based system may not handle that flexibility unless additional rules have been created in advance. As the number of rules grows, maintenance becomes more difficult. Rules can overlap, conflict, or create unexpected interactions, and the knowledge base can become hard to manage. This is one reason symbolic AI systems can be powerful within boundaries, but difficult to scale across open-ended environments. So the balanced assessment is that symbolic reasoning provides powerful reasoning capabilities within structured domains. It gives AI systems a way to represent knowledge explicitly, reason consistently, explain conclusions, and encode expert decision-making. At the same time, it depends on carefully designed knowledge structures and can struggle with uncertainty, ambiguity, and change. This does not make symbolic reasoning obsolete. It means we should understand what it is designed to do well and where other approaches may be needed. As you evaluate symbolic reasoning, focus on that balance. Its strength comes from structure, but its limitations also come from structure. The same clarity that makes it explainable can make it rigid, and the same rules that make it consistent can make it less responsive when the real world refuses to fit cleanly into predefined categories.